Hello, my name is Sam Sudley, and this is my Physics 1 Lab 1, which explores the idea of constant velocity. So, an introduction to what this lab was, its purpose was to compare the position of a rolling ball at constant velocity, both computationally and experimentally, and see if there was a difference between the two. So, for this experiment, I chose my object to be a rolling pickleball. For my experimental data, I used the tracker app, and for my computational data, I used the app GlowScript. So Newton's second law is also known as the momentum principle, and what it basically states is that the net force on an object is equal to the change momentum of the object over the change in time. So if you derive this formula, you can generate the momentum update formula, which is shown here, which is the final momentum is equal to the initial momentum plus the net force times delta t. And if you derive this formula further, it yields this equation, which is the velocity update formula, which basically gives you that the final velocity is equal to the initial velocity plus the net force over the mass delta t. So this equation is used it's very useful to finding the updated velocity of objects. So the lab procedure for the specific lab experiment is as follows. So the first part was to capture a video of an object rolling. In my case, it was the pickleball in a straight line at a constant speed. And then second, we imported the video into the tracker application to track the change in position of the ball on a frame-to-frame period for a certain time t. Third, we used the GlowScript application to create a computational model of the same ball rolling in a straight line at a constant velocity for t seconds. And then we plotted the data of both the tracker model and the GlowScript model to compare the outcomes of the experiment. So here is the tracker model. And as you can see, the ball's rolling. Each of those little diamonds is a position that's being tracked by the application. And then you can see the position versus time graph in the top right. And it appears that this creates a linear position versus time graph slope, also known as the velocity, which would generate the idea that it's a constant velocity. So this generates an analysis of the experimental results. So as you can see here, we have the first two time increments, which gives us the total time from the first position to the second position. And then using the delta t formula, we find that from the first position to the second position, it was 0.033 seconds. Using this, we can find the initial position, which was actually given to us in the graph, which was just the first position recorded. And then using both of these values, we can find the initial velocity by subtracting the final position minus the initial position over time 2 minus time 1, which gives us this as the initial velocity of the ball. So computational analysis, first we have that the mass of the ball was 1, and given the velocity update formula, if the net force is 0, that means the mass also cancels, so this didn't really have an effect on our model. Second, I inputted the position vector and the initial velocity vector as we computed in the previous slide, and then delta t was 1 over 30 because the iPhone records at 30 frames per second. The net force on the vector was obviously 0 because if you have a constant velocity, that's going to be 0. And then here are the position update and velocity update formulas. And this computation analysis generated this graph. So as you can see, there is a difference between the experimental data and the computational data. And what could have caused these deviations? Primarily, number one, position tracker. There could have been errors in placing the trackers at even increments. There could also have been rounding errors, and outside forces such as friction, air resistance, and things like that could have also made the experimental data not be equivalent to the computational data. Additional questions. So what if the negative x and positive x axes were interchanged? If they were interchanged, then the slope of the position versus time graph would be negative instead of positive like we saw with the results. Is the net force really 0? No, there are other forces such as friction and air resistance that create a non-zero net force, which explains the deviations in the two data points.